In section 6.1, we're going to be interested in trying to find the area between two curves. So, for instance, we'll take a look at this first one, trying to find the area between two curves, these two curves. So it's this area that we're trying to find. And let's think about how we're going to do that. Well, the way we can work on this is to try and approach it with Riemann sums like we did back in section 5.3, 5.2 actually, and try and approximate this area with some rectangles. So how would that work? Well, what we're going to do is take a closer look at it on, you get the same thing on your handout, but this at least looks like it's got some color to it. We're going to divide up this interval from A to B into a bunch of different subintervals, have them all be the same width, so we'll call that width delta x. They don't necessarily need to be the same width. You could have them varied widths. So in this diagram, it's subscripted with delta x sub k, but for us, it's just going to all be the same. Let's concentrate first of all on finding the area of one of these rectangles. Now, the area of one of these rectangles, like any rectangle, is going to be given by the height times the width. So let's think about the width first. So the area of one rectangle is what we're looking for. Area of one rectangle is going to be the height times the width. The width, that's just going to be pretty easy. That's going to be a delta x. But how about the height? How are we going to get the height of this rectangle? Well, we're going to have to measure a couple things. We're going to have to measure where we're at in terms of the function for f in this interval, and then subtract off the value of the function for g at that same point. So it's going to look something like this. F of x sub k star minus g of x sub k star. And that's going to be the area of one rectangle. Now, if you want the area of all those rectangles, then you're going to sum it up from k equals 1 to n. All right, that's well and good. We're going to skip a lot of this stuff as we actually do these problems. But let's see what we can do once we've got that summation. So when we got that summation, it's going to look kind of like this. Do you think that's a really good approximation of the actual area between these two things? Right now, probably not so much. What could we do to make this a little bit better, improve this approximation? Anything? Make the rectangle smaller. Thank you. Yeah, let's make the rectangle smaller. So we'll add more rectangles. So a few like this. Okay, is that better? Yeah, a little bit. Is it good? Probably not. Probably not that great. So let's keep going, right? Keep on adding more and more rectangles. What's this process of adding more and more rectangles really kind of doing mathematically? What are we doing? Yeah, we're taking the limit. As the number of rectangles n goes to infinity, we're taking the limit. And as you take the limit, it gets to be a better and better approximation of the area between these two. And in the limit, that sum, that Riemann sum, becomes the Riemann integral. So what you're going to end up with is the area between these two curves is really going to be the Riemann integral of the difference of these two curves in the appropriate interval. Oops. Sorry, let's try that again. It's going to be the difference of the two curves in that interval. So to figure this area out, here's the integral we're going to have to calculate. It's going to be the integral of f of x minus g of x, in this case e to the x minus x e to the x squared, which looks like kind of a wild thing. So that's really this part right here, f of x minus g of x. That delta x, if you remember, delta x is interchangeable with what other notation that we use? Dx. Great. And last but not least, that dx kind of helps us out a little bit because it reminds us that we're doing this with respect to x. So a lot of times when I do this, I'll just draw a little slice here and say, all right, we want to find the area of that one slice. That's going to be your top minus bottom. So top minus bottom, great. We've got the area of that one slice. Now we need to account for the interval over which that can be taken. So the lowest value that I can use for x, where this is still going to be inside my shaded region, is going to be at 0. But how far up can I go? How far can I go and still be within that shaded region? So what's the top value for x? 1. So there you go. So that's how we have to calculate the area between these two things. Now, that's as far to the left that I can go and still be in the shaded region. So I want to try and find the area between the two curves and the y-axis. So the y-axis gives you kind of a boundary for the curve, or the region. And the other boundary is where those two things meet. Does that help?
So it wouldn't be, because where the red dot is, it wouldn't be.
So the x-coordinate at the red dot is 1.
Okay.
Yeah.
I see that.
All right, good, good. So the setup is certainly a good portion of the points that you can earn on a problem like this. Let's finish this off by actually calculating that integral. So this is example A. And it's a little bit harder than, you know, maybe your typical first problem for an introduction to this kind of stuff. But it gives us a chance to review some stuff that we did in section 5.5. Now, what might be helpful for you would be to break this up into two integrals. The integral from 0 to 1 of e to the x dx minus the integral from 0 to 1 of x e to the x squared dx. So nothing earth-shattering there. Well, the fundamental theorem of calculus part 2 says we need to find an antiderivative for e to the x. What's that antiderivative? E to the x. That's kind of nice. So let's just e to the x between 0 and 1 minus this thing, and that one's going to require some work. So let's see about doing some of the work on that. How am I going to find an antiderivative for that one? If you're looking at me saying, well, I don't know, you didn't cover that one. You're right. I didn't cover something like this. But that's because there isn't one directly. What do you suppose we have to do on that one? Yeah, well done. We have to use the u substitution. So let's see. Suggestions as to what to let u equal. And I'll let you think about that for a second. If you're watching this later, pause this. Try and figure out, what should I let u equal? Share your idea with your neighbor. Do you agree with your neighbor? What should I let u equal? All right. One thing that can catch your attention is you've got an x squared term here. Why would that catch your attention? What happens when you differentiate an x squared term? Yeah, you're going to get a 2x. basically the degree is going to decrease by 1. So we're going to have some power of x, actually to the first power of x. And you've got an x here. So when you see stuff like that, you know, a degree 4 here and a degree 3 here, then you can start thinking that, hey, that looks like a pretty good candidate for our u substitution. So we'll let u equal x squared, and then du by dx equals 2x. Now, a lot of you would probably just jump right away, skip this step, and write du equals 2x dx, and that's fine. Nothing wrong with that. But that's not quite what I have up here in this integral, is it? I've got an x and a dx, but I don't have that 2. So let's just underline what I've got. What can I do with that 2 that's out in front there?
Make it half.
Yeah. I'll multiply both sides by the reciprocal. And as Yura suggested, we're going to make that a half on the left-hand side. There's one last thing that I personally like to do when I'm working on these problems, and that is I'm going to think of this as, say, u of x. I want to change the limits of integration here. So what are the new limits of integration going to be? Well, I've got to plug in a couple numbers. And it's going to look funny in this one because we're not going to see much of a change, are we? So our limits are the same. Now generally that doesn't happen when you do these problems, but it does in this case. That's fine. Wow, we did a lot of work here in order to find an antiderivative, but that's just what you need to do here. So let's take a look. This becomes the integral from 0 to 1, and it's the new units, even though it looks like the old units, of e to the u, and then the x dx gets replaced by 1/2 du. So 1/2 du. I can take that 1/2 out in front, and let's see, I got 0 to 1 e to the x minus 1/2 the integral 0 to 1 e to the u du. And like our first part of this problem, we need the antiderivative for this thing. So 0 to 1 e to the x minus 1/2 the integral from, or it's going to be the function from 0 to 1 of e to the u. Okay, finally, let's do some evaluation here. Let's plug in the 1 here. It's going to give me e to the first power minus e to the 0 minus 1/2 e to the first power e to the 0. And let me make maybe a clever observation here for us. These two binomial terms are the same. So what I'm going to do is I'm going to do part of my work here just by subtracting these two. 1 minus 1/2 gives me 1/2 of e to the first power minus e to the 0. What's e to the 0 power? 1. So e to the first power minus 1, or just e minus 1. There's a nice exact answer. Great. Nailed it. Comments on that one? Looking okay there? All right. Let's take a look at example B here. Now, example B, I'm going to start something that I'm going to continue in the next section as well, and that is I'm going to approach this by taking a slice through this and calculating the area of one slice. So let's take a look here. This is what's called a dx slice, because dx is the thickness of that slice. So here, so that's dx. And I want to find the area of that one slice. Well, let's see about that. Area of one slice. Well, the area is simply going to be the height times the width. So it's nice to give it a very tangible geometric interpretation. And let's see, I've got a couple different functions here. Which one's this top function? Your choices are e to the x, y equals x squared minus 1, and then I've got negative 1 and 1. Those terms, that just helps us define some of our region. So x equal negative 1, that's this little part right here. And x equal positive 1 is the right-hand side of this figure. What's the height? How am I going to calculate the height? And by the way, which curve is this? This top one. Yeah, that's y equals e to the x. The parabola shape is down here. Y equals x squared minus 1. So the height is just going to be the top minus the bottom. Okay. So top minus bottom times the width. The width is dx. We're taking a dx slice there, so let's put that in right away. Our top function is e to the x. And if you're not careful, you might write something like this. X squared minus 1 dx. What's wrong with that? You need parentheses around it. That, or you need to distribute the negatives. So you need parentheses around that. That's perfect. That's what we needed to get to, is the area of one slice. Now what? Well, now we want to add up the area of all such slices. Now technically, that's a limit process, and what we really should be doing is writing the Riemann sum, taking the limit, etc. But we're just going to kind of bypass that. We're just going to jump to the integral. So it'll be the integral of e to the x minus x squared plus 1 dx. But what about my limits? My limits come from where I can move this rectangle. How far to the left, how far to the right, and still stay within this region. So what are my limits? Lower limits and upper limit. Thank you. Minus 1 to 1. Nice. Now this is a symmetric interval. What you might want to look out for is whether or not this is an even function or an odd function. If it's an odd function or an even function on that symmetric interval, there's some shortcuts that we discussed last time. This one's a neither. It's not an even function, it's not an odd function, so we're just kind of stuck. Let's see about finding the rest of this then. I need an antiderivative. We're done with the integral. Don't write this integral symbol anymore. It's negative 1 to 1 of e to the x minus what? What are my other two terms here? Thank you. X to the third over 3 plus x. Now it's a matter of crunching some things in here. So let's see. At 1, I'll get e to the first power minus 1/3 plus 1 minus e to the negative first power minus negative 1/3 minus 1. So let's try and be careful with some of the arithmetic here. E plus 2/3 minus e to the negative first. These two are going to cancel each other out. So I'll have a plus 1/3, and then a minus 1 is going to give me a minus 2/3. Let's distribute. When I distribute, that becomes a positive 2/3 plus this 2/3. I'll end up with e to the first power minus e to the negative first power plus 4/3. That's a nice exact answer. Yay. Very happy with that one. So, okay. Got a nice exact answer. What if you wanted to check it? What if you're like, yeah, I kind of want to check that one? What could you do? Well, your calculator is not going to tell you the exact answer, but it will tell you a decimal approximation. So you could bust out the calculator and make sure that it works. So let's just double check it. I mean, I really encourage you to do that double checking because you can catch some mistakes. Maybe I made a mistake. Who knows? Let's figure it out. So it's math 9. Destined to become your best friend. -1 to 1. E to the x. Let's see, where else we got? Minus x squared plus 1. And your calculator insists on the dx. You know what? I made a mistake here, didn't I? That's all in the exponent. Sometimes I get in my own little world. All right, e to the x plus x squared plus 1. Your calculator insists on that dx, so do I. That becomes important a little bit later, especially in Calc 2. And bam. Let's compare that to e. It took me an embarrassing long time to discover that, oh, that's just the e if I want it, plus e to the negative first, -1, plus 4/3. Actually, it should be a minus. Let's make that a minus and hold our breaths. Uh-oh. Something. What's that?
It's minus x squared on the top.
It's minus x squared? Oh, okay. Thank you. So let's go back there and figure that one out. Yeah, minus x squared. Thank you. Whew. I thought I was wrong, but I was merely mistaken. Nice. Nice. All right, so we nailed it. Now, like I said, on the exams, I typically ask for exact answers, but there's nothing that prevents you from checking your answers. So take advantage of that. I mean, how many classes can you check your answers before you hand in the exam? Probably not that many. Okay, let's move on to example C here. So in these first couple examples, you're kind of gifted a little bit because I gave you the limits of integration, or the figure pretty much told you the limits of integration, but that's not always going to be the case. Such is the case in example C. It says find the area between the two curves, x squared minus 2x and 5x. So certainly y equals 5x is going to be the straight line here. I want to find the area between the two curves, so that's this little piece right here. So you get kind of this little sliver right there. And let's see. Well, we'll do the same thing we did before. We're going to approach this with a dx slice. Take a little slice right through that region and see about finding the area of that one slice. So that has a thickness of dx. Area, move this up, area of one slice. So the area is going to equal the top minus the bottom. That basically gives you the height times the thickness, which is our dx. Once you have that dx there, that's telling you that both of these have to be in terms of x. We can't integrate in terms of y if we have a dx there. So top minus bottom, Our top function is clearly going to be the line, which is our 5x, minus, again, let's be careful with the parentheses, x squared minus 2x dx. Okay. If you distribute and collect like terms, how does this simplify? Thank you. 7x minus x squared dx. Now that's the area of one of these rectangles. I need the area of all these rectangles. So that's going to be an integral of 7x minus x squared dx. I can tell you the lower limit, that's going to be a 0. But what about the upper limit? If you don't feel like counting, if you can't necessarily tell by your graph or something like that, then you've got a couple choices. One choice is to solve this equation, or solve for where these two equal each other. So that would be like this. I want the y coordinates to be equal to each other. So I get x squared minus 5x equals, x squared minus 2x equals 5x. 2x equals 5x. If I move this to the other side, I get x squared minus 7x equals 0. Hopefully you don't bust out the quadratic formula on that one. Just factor out an x minus 7 equals 0. And I can see that either x equals 0 or x equals 7. That's the points where these two curves are going to have the same y coordinate. That's where they're going to meet. So that's going to be your upper limit right there. Do you recognize what kind of function this is? Ooh. All right. Let's find the antiderivative then. That's going to be 7x squared over 2 minus x cubed over 3 between 0 and 7. As I plug in those limits, plugging in a 7, I get 7 times 7 squared. 7 to the third power is 343 over 2 minus 343 over 3. So that's plugging in x equals 7. If I plug in a 0, I just get 0. And if you do the arithmetic here, I believe you're going to get 343 over 6 when you get common denominators and finish subtracting. Yay, a nice exact answer. So the reason I was asking you about, do you recognize this? For polynomials, I'll probably generally allow you to finish this up with fn int. I'm not really interested in making you do all this arithmetic here and risking you losing some points because you made a mistake with the arithmetic. So if it's a polynomial, on an exam, probably I'll let you do fn int to finish it up. Now if it has some other terms in it, like a sine or a cosine or e to the x, something like that, then you'll probably end up having to find the antiderivative to finish this up. Okay, how are we looking on that one? Let's move on to example D here. So we want to find the region enclosed by these two curves. So let's shade that region first. Wow, I somewhat managed to stay between the lines. I was never very good at that. Now I keep on talking a lot about we're taking a dx slice, taking a dx slice. Do you always want to take a dx slice? Maybe yes, maybe no. It kind of depends. If we look back at example B for just a moment, let's see what would happen if I tried to take a dy slice. So what do you think a dy slice is going to look like? If I'm trying to find this with a dy slice. Yeah, it's going to be horizontal. Except we're going to run into a problem trying to take a horizontal slice through this region. So if we're trying to take a horizontal slice, well, let's see. We'll do it here. Now you can still find the area instead of subtracting two functions vertically. We're going to subtract two functions horizontally. And it's going to be the rightmost endpoint minus the leftmost endpoint. But there's a problem. There's actually several problems. And that is the width of your slice kind of changes, doesn't it? It's not just always this minus this. It's not always 1 minus e to the x. Down here, it's 1 minus -1. Down here, it's, well, the function to itself. So hopefully you can see the problem that you can run into with your trying to take a dy slice. It just doesn't work out that good because you'd have to end up setting up 3 integrals, one for each different, width of your slice, if you wanted to do it with a dy slice. So it'd be most inconvenient to do this with a dy slice. In particular, if whatever slice you're taking goes from a function to itself, then that's really, really challenging. I wouldn't necessarily try and do it that way. You might want to try and take a slice in a different direction. Now, in this particular case, if we take a slice in the vertical direction, yeah, that's looking pretty good. So we'll take a dx slice there. Now that dx slice isn't going to change as you're moving from right to left or left to right across this figure. It's always still going to be this top function minus this bottom function. So let me just make that a little bit more official here. So there's our dx slice. Let's set it up to find the area of this integral. I want the area of one slice. Area of one slice. Why don't you set that up? Set up top minus bottom. Try and find the area expression of one slice. Well, I guess it's helpful to make sure you know which one's the top and which one's the bottom function. So let's do that. Let's add that to our little picture here. Which one's the top function? The orange one or the pink one? The orange one. Yeah. You're going to have a parabola that faces down. So that's this one here. And then the other one's a parabola that faces up. That one there. So top minus bottom is going to look like this. It's going to be 16 minus x squared minus, in parentheses, x squared minus 2 times the thickness times the width, dx. Now this should simplify, right? How does that simplify? well, let's see, if you distribute the negative, that's going to become a positive 2. Positive 2 and 16 gives me 18. 18 minus what? Thank you, 2x squared. So that's the area of one slice. But Derek, we're going to run into a problem. How far over can I take these slices? From what to what? Kind of tough to tell, right? Oh, well done. Did you actually solve that? Okay, good, good. All right, I thought you were just eyeballing this and somehow coming up with it. I deliberately left the units off of this so that you would have to do something like solve it. And solving it is what we'll do. Now keep in mind, you can solve this with your graphing calculator. I don't want you to overlook that if you really needed to. Now, you don't necessarily have a problem like this. We will in example F, so I'm not going to bother with it now. But if you look underneath the calculate menu, one of the things that'll help you find is a point of intersection. So you always got that as a backup. All right, let me come back here. I'll finish up example D here. Example D. So I want the integral. Well, this point is at -3, and this point is at 3. Again, like I said, you can solve that. It's going to be where 16 minus x squared equals x squared minus 2. If I move everything to the right-hand side, well, actually, you know what? I'll move the x squared to the right-hand side and the 2 to the left-hand side. I end up with 18 equals 2x squared. So 9 equals x squared, and plus or minus 3 equals x. So those are going to be my limits, -3 to 3. -3 to 3 of 18 minus 2x squared dx. There is something I want to point out about this problem. Now, it's not a big deal, but it is kind of helpful. If you've got an even function over a symmetric interval, well, there's a little bit that you can do to save yourself some work. It's not a huge deal in this problem, but if you take a look, the left-hand side of this and the right-hand side of this, those are going to have the same area. So what we'll do is we'll just calculate it once. We'll just calculate from 0 to 3 of 18 minus 2x squared dx. But what do I have to do to kind of compensate for that fact? Multiply by 2. So don't forget that little part there. Let's skip spending time on the integration part. I think the answer here, when we're all said and done, is going to be a nice even 72. I want to spend more of our time focused on actually setting these things up and getting those things going. Derek.
Why did you multiply by 2?
If you take a look, I changed the limits of integration. This is an even function, so instead of, doing this area and then this area, both of which are the same, I just did them once and then multiply by 2. The savings a lot of times it's a lot easier to plug in 0 into a lot of expressions than actually plugging in a number like -3. So you get a little savings. The real savings is when you have your odd function. You remember what happens when you have an odd function. If you have f of x equals an odd function and you're integrating from negative a to a of f of x dx. What happens with your odd functions? Yeah, you get a nice big goose egg. Let's put that in some color here to make it pop a little bit. Yeah, you get a nice big goose egg. So that's a nice feature. If you can recognize you've got an odd function over a symmetric interval, it'll really save you a lot of time. A lot of times I'll put like one of them on an exam. Some people see it, some people don't. You know, I understand if you don't. If you don't, then you'll end up with 0, and you look back and go, oh, man, bummer. But no big deal. Okay, looking good on example D. Let's try example E here. I want to find the area between these two curves. The first of which is y equals x cubed. Second which is y equals x. And bingo. So y equals x cubed, clearly that's going to be the curve with a little more shape to it. Then I've got my other curve, which is simply y equals x. That's going to bisect the first and third quadrants. So that one right there. I want to find the area between these two curves. Now, I'll give you a heads up. All your answers, and I mean all your answers in this section, should be positive numbers. That's because you're trying to find an area. Now, I know that sometimes when curves dip below the x-axis and you're integrating, then you get a negative number. That's okay. It's different because what you're getting is a signed area. It's telling you that part of your area is below the x-axis. That's okay. But if you're strictly trying to find the area between two curves, it should be a positive number, period. If you get something other than a positive number, there's something that's wrong. So let's take a little dx slice here. Dea, question? So here's our dx slice. Try and set up the area of one slice. Oh, that's going to come out in the this is going to come out in the wash. All right, but good on you for spotting that. So top minus bottom. In this case, the top function has to be x minus the bottom function, which is your x cubed. So x cubed dx, looking good. If we want to add the area, find the area of all such slices, then you can integrate from -1 to 1 of x minus x cubed dx. Why don't you try and do that with fn int? See what happens when you do that with fn int. So let me get rid of this and this. Oh, my ride's here. I gotta go. All right. Hopefully somebody's gonna be okay. Math 9, -1 to 1, x minus x cubed dx. Can anyone anticipate something that's going to happen here? 0. You've got an odd function over a symmetric interval. Well, how am I getting an area of 0 when I know that area has to be positive? So the girls over here have kind of figured it out. How about anyone else? What else you got? What you got going there? What did I do wrong that I got a 0? Looks good to me. Girls, want to enlighten? What happened? Somebody got over here? Robert, what's going on?
I was just going to say that if you take the dx slice to the left of 0, the top function is x over
Oh, yeah. If you take another dx slice, say over here, then the area of one slice is going to change, right? Your top and bottom function interchange. So the area of one slice here is going to be x cubed minus x dx, whereas the area of one slice over here is different. So you've got a couple choices as to how you calculate this thing. So one of them would be to split up the integral into two integrals and write it like this. So that gives us 0. We know that's wrong. So we write it as -1 to 0 of x cubed minus x dx plus the integral from 0 to 1 of x minus x cubed dx. So that'd be one way to do it. Is there another way to do it? What do you think about those two areas? They're the same. So you could calculate it as twice, say, this one, integral from 0 to 1 of x minus x cubed dx. And so that's what I'll do. That'll be my quick fix on this. So let's go back to our previous calculation. I'll hit the second key, then the enter key. That'll bring up my previous calculation. I need to, multiply that by 2 and change one of the limits. So let's change that lower limit. I'll make that a 0. And I'm not sure if you're aware of this, but there's a little insert key right here. If you hit the second button and then the delete key, up on top is your insert key. I'll just put a 2 out in front there so I don't forget it. Twice that gives me 0.5. So kind of a slender little area there, but area nonetheless. At least it's positive now, right? So happy about that. Elias, is there something about this that's troubling you? Is that looking good, or is there some detail I can add? So to kind of recap here, when we first did this, charging ahead naively, we said, oh, well, wait a minute, we got a 0. That shouldn't happen. And we realized when you're doing this with a dx slice that, yeah, your top and bottom functions change throughout the interval. So we had to split it up. If you did it this way, this interval would be, or this integral would give you a 1/4, and this one would give you 1/4. Add them together and you get your 1/2. All right, so please do be aware that you should get a positive number there. Yes, Natasha.
So do the areas not cancel out, or does that take into account the sign differences?
Like this thing?
Yeah.
Both of these should be positive areas now because we're calculating it in the proper direction. Top minus bottom is going to give you a positive number for the height, and then you're integrating that positive number throughout this interval. So you're going to get a nice positive number there.
Okay.
What happened when we first did it is for part of this interval, when you're calculating this minus this, you're getting a negative number in this part, and that negative area is going to balance with that. So that's what happened with that first part.
Okay.
We needed to change the order of our subtraction.
So if we do it like the first part, it's wrong, right?
Yeah, if you just do it in the first way, that'd be wrong. But hopefully this would be screaming out at you that there's something wrong, because you're not going to get a 0 answer for a problem like this. Your area problems in section 6.1 should all be positive. Okay, we've just kind of danced around a little bit. Let's work on doing one numerically. And that's going to include a couple things. So we're going to try and find the area between these two curves. So that's the area we're looking at. Hopefully everyone's got a graphing calculator today. I'll I'll be honest, I'm not entirely sure which one's which. I'm thinking that this first one is this one right here, but I don't really know. We don't have to know right at this moment. We can still solve this with a dx slice. So I'll take a dx slice here. Maybe bigger than I needed, but that's okay. I want to find the area of one slice. Let's put that on our graphing calculator first, so we can determine which function is which. So I'll go to the y equals menu, and let's type in sine of x over 1 plus x squared. If you want to get a little bit fancy, you can use the fraction bar. On some of your calculators, right next to link, if you see a little green, circle, square divided by another green square, then you can hit the alpha and the X key, and that'll give you a nice quick way to access the fraction menu. Sine of x divided by 1 plus x squared. And then the second one, I'll do likewise. Alpha here, x squared. Let's see, x squared. Help if I put in the square there, or the x. Let's just clear that out and start all over. So alpha here, I want, is that x cubed divided by, let's see. Oh, it's an x squared divided by 1 plus x cubed. So x squared divided by 1 plus x cubed. Let's kind of mimic what I see in terms of our graph here for our window settings. So I want to go from like 0 to 0.9 should be fine on the x-axis, and say 0 to 0.5 on the y-axis. So for my window settings, let's go there next. 0 to 0.9 on the x-axis. If you want, you can make x scale something a little bit more reasonable, like maybe 0.25. That way it gives you a little better sense of where you're at. On the y-axis, 0 to 0.5 should be pretty good. And then hit the graph key. Great. So a pretty good representation of what we got. We can now tell which graph is which because they're color coded. If you look back at your y equals key, the sine of x over 1 plus x squared, that's the blue one. So that's our top function. Let's kind of take note of that this way. Here's your top function. So I'll code it like that. And then here's your bottom function. So let's see if we can't set up the formula for the area of one rectangle. Area of one rectangle. Give yourself a second to see if you can't set that up. See what you can do. If you haven't already put these two functions into your calculator, please do so now. I'm going to show you kind of a cool trick that'll save us a little bit of time here. And you're also going to want to practice some of what we're going to do here. It's a good skill to be able to do. Now I've got a lot of the steps and things like that on our handouts. So if you needed to look back at this stuff later, you've got all this stuff here that we're going to be doing, but try and keep up with it now while you've got some narration and some help here. James, what's going to be the area of one of these rectangles? All right. Mm-hmm.
x squared over 1 plus x cubed dx.
Nice. Nice. All right, so that's the area of one rectangle. Let's set this up in terms of an integral now. So in terms of an integral, I'm going to integrate that exact difference. Thanks again, James. Sine of x over 1 plus x squared minus x squared over 1 plus x cubed. And let's put that in parentheses and put a dx here. But what problem am I going to run into next? Limits. Tell you what, I'll give you one of them. That'd be 0. Yeah, I'm so helpful. I know it. But what about that upper limit? How am I going to find that upper limit? I'll tell you this. I couldn't solve for it analytically. There's no quadratic formula or something like that that you could do here. I don't really feel like busting out Newton's method. That would just be horrendous here. So what can we do? Sidra? Yeah, just use the calculator. So if we go to the calculator, then one of the things that's open to you is the calculate menu. And on that calculate menu, oh, there's intersection. Great. Let's use the intersection of those 2 points. Now it's going to ask you for a couple things. It's going to ask you to kind of estimate that intersection on the first curve. So just kind of cursor over, somewhat close to that intersection point. And when you get reasonably close, you're going to end up pressing enter a total of 3 times. Once for the first curve, once for the second curve, once for reasons that I don't really know. But that's what I asked for you. So you should get about 0.8273, etc., etc. So nice. So you're going to want to write down that number. Not really, I'm kidding. Yes, go ahead.
Sorry, could you show that one more time?
Sure. So one more look at that. You're going to hit the second key, then the trace key that takes you to the calculate menu. You want option 5. So let's pick option 5. For option 5, you're going to end up having to try and approximate this by moving your cursor close, and it doesn't matter exactly where. Let me move to the right of their point of intersection, but just reasonably close. Now it's going to ask you to press enter a total of 3 times. Once to give an estimate of that intersection on the first curve, once again for the second curve, once again for reasons that I can't really explain. But that gives you your number. So about 0.827 is what you want. 0.827. All right, that's great. Now we're going to have our calculator do this limit or this integral numerically. So here's where I want you to really keep up with this, and hopefully you have. Let's go back. I'm going to clear this out. How do I get my numerical integration? Math 9, right? Your new favorite keys. Math 9. You know what? Let me just show you something that's kind of cool here for a second. Don't stop what you're doing, or don't type anything at the moment. The one cool thing about your graph and the work we did, see that point's already gone? But the cool thing is that your calculator stored that value in X. There's your values. You don't even have to really write it down. So when I go back and I do my Math 9 stuff, let's see, Math 9, my limits are going to be 0 to X. And it doesn't hurt to put that X there, even though we're using the X's here. Now, raise your hand if you feel like typing in those expressions again. All right, good. James is giving me a definite no. I'd rather eat lima beans. All right, so let's do something other than that. You can go to the vars key and then to yvars. Press enter. Function y1 minus function y2. So I'm going to go back and repeat that again. Vars, yvars, function, and then 2. and dx. So once you do that, bam, there's your answer. So it's all digital at this point. So kind of nice that you can do that. How many people were actually able to get that number on their calculator? Wow, that's a good lot of you. Well done, well done. Hopefully the rest of you can either reach out with a question or try and get some help. But that's a good skill. That's something that I wouldn't mind doing on an exam, is testing you that way. Because realistically, a lot of the functions that you're going to deal with outside of this, and maybe in a physics class or engineering class, you're not going to be able to find an antiderivative for this one. You can't find an antiderivative for that. You just can't. You can for this one, and the hint for this one would be you've got a cube here and you got a squared here. This is one lower than this. So if you let u equal 1 plus x cubed, your du term is going to have an x squared. And you could end up integrating that using the log function. All right. So a lot going on with that one. Any wrap-ups or any other comments on that one? All right, let's do a couple more to kind of finish this off. And we're going to go back to the dx versus dy debate. So this time we've got a couple different functions. X equals y squared minus 3, and x equals e to the y. So that x equals e to the y term is going to be this function right here. We want to find this area. If you take a dx slice, then you're going to run into problems. Let's see if we can understand the problems here. If I take a dx slice here, I get one set of top and bottom functions. And then a dx slice a little bit over from that, right here, I get another set of top and bottom functions. Now, in this case, it's not such a bad thing because, I mean, with this middle dx slice, because it's just a constant height there, so that's not a big deal. But what's a real big tip-off for you that this dx slice is not necessarily a good idea is this one right here. Because now, if you're trying to measure the height, you're going from a curve to itself. So that's generally going to be more difficult depending on the curve. So you want to avoid that. So avoid going from a curve to itself with a dx slice, or with any slice. You want to avoid that. Does doing a dy slice help out? Well, let's find out. Let's see. Move out a little bit. So let's take a look at this one here. Like this. And a dy slice is going to be right here. So let's do our nice dy slice. So here's dy, here's dx, dx, and dx. Does that dy slice change from one region to the next as you go up and down here? Or is it still always the same right minus left in terms of the thickness?
It's the same.
It's the same. Let me see, I think I got a, let's see, thought I had a link to demonstrate that. Let me just take a look back here. No, that's not it. Yeah, this one. So here's kind of like the next example showing that, but in this region, the dx slice changes from one side of this curve to the left of x equal 2 versus to the right of x equal 2. The dx and the dy slice are going to be a lot different. The dx slice, you need two integrals to do this. If I change this up a little bit, let's get rid of those. Let's take a look at the dy slice. The thing about the dy slice is that it's always the right minus the left. Doesn't matter where you're at in terms of its height. You're always still looking at the same two curves when you're finding your distance from right minus left. So that's going to be much better because we'll only have to set up one integral as opposed to two integrals. So let's do that. Let's do our dy slice here and find the area of one slice. Now the area of one slice is going to look a little different in this one. Instead of top minus bottom, you're going to replace top minus bottom with right minus left. Right minus left. In this case, we're also going to multiply by the thickness. What's the thickness of that slice? Yeah, it's a dy thickness. And because this is dy, that's telling you that your expressions for the right and the left better be functions of y. Fortunately, they are. The rightmost function, that's e to the y. So you've got x equal e to the y. So that's going to be my rightmost function. Let's put that in here. E to the y. And the leftmost function is this one over here, y squared minus 3. So I want to subtract right minus left. Again, you got to be careful with the parentheses. Y squared minus 3. But there we go. There's your expression for the area of one slice. So to finish that off, you would end up integrating from, say, something to something. We'll have to figure that out in a second. E to the y minus y squared plus 3 dy. And if you notice, I distributed that negative sign. What will limits of integration be? Think about where your slice can go. What's the highest? What's the lowest? To still be in the region, it'd be -1 is the lowest you can go, and the highest would be +1. Yay. All right. The rest of this you can finish up as needed. I do want to do this one last one here, give you a chance to try and set one up on your own. Our two functions here are x equal y and 8 equals 2x plus y squared. So this is going to be our 2x plus y squared equals 8. Now I will give you a little bit of a heads up here. You're going to need to solve for x. So if you were to solve for x, it'd be x equals 1/2 times 8 minus y squared. You can distribute the 1/2 if you want. Doesn't matter. If you want to write it as 4 minus y squared over 2, that's fine. But see what you can't do to set up that integral. We're going to try and find this area enclosed by these two regions, or these two curves. Bless you. A magic pause button.
That's just an expression for x, so that's telling me the x coordinate is 4 minus y squared over 2. So that'd be the rightmost function. This is x. This is y. So where is my total y? Slice here.
All right. So let's see if we can't put some of this together a little bit. The big thing to take note of is that we're using a dy slice here. So when you're using a dy slice, the area of one slice is going to be right minus left times the thickness. So in terms of right minus left, so right minus left times the thickness is our dy. Now really what you're doing is you're subtracting the x coordinates. The x coordinate here minus the x coordinate here. But because I want this in terms of y, because I'm taking a dy slice, I realize that my x coordinate for any point here is going to be 4 minus y squared over 2. So that's going to be my rightmost point here. 4 minus y squared over 2 minus the leftmost point. Now the leftmost point is going to have a coordinate of x, but x is also equal to y. So I'll have something like that. 4 minus y squared over 2 minus y. Now you could have also used this expression, or you could just write it as 8 minus y squared over 2. Whatever works for you. But that's the area of one slice. Now I want to add up the area of all such possible slices. So I got to think about how low I can go with that slice or how high I can go with that slice. But that means I need to know a couple answers. I need to know the points of intersection here and here. How am I going to find those? You could do it with a calculator, although it might take a little bit more work than usual because you'd have to solve for y, which means a square root, and there's a plus or minus. You'd have to graph those separately. It'd be a pain. Yeah, let's set them equal to each other. In fact, this is tailor-made for the method of substitution. You've got x equal y. And if I look over here, well, it'd be nice if I got rid of, say, one of those. Doesn't matter which. You want to get rid of the x, or we're going to get rid of the y. Let's get rid of the y. Let's get rid of the x, just for giggles. So with our substitution, that's going to be a 2y plus y squared equals 8, or y squared plus 2y minus 8 equals 0. And that's going to factor. How's that factor? Yeah, y plus 4, y minus 2. So that gives me my two solutions, negative 4 and 2. Thanks, Robert. So, yay. Negative 4 and 2. So this point would be negative 4 and 4. And this one would be 2 and 2. Because y is equal to x along this line. So that's where you're getting that other unknown x value. Great. That's going to allow me to finish this up with an integral. What's that integral going to be? Well, it's going to be this one. The integral of 4 minus y squared over 2 minus y dy. What about my limits of integration? What should those be? Negative 4 is as low as this can go, and as high as it can go and still be inside my region would be a 2. And let's finish this up with the graphing calculator. This is, after all, just a polynomial. And what I do a lot of times to try and save you some time on these problems is, let you set it up with, set it up here and then finish it with fn int. So I want math 9 from negative 4 to 2. Now when you type it in, you don't have to, be all fancy and type it in with y's. Just type it in with x's. 4 minus 0.5 x squared minus x, and then of course dx. You could take the time to do it in terms of x's, or in terms of y's, but why bother? We end up with 18. Awesome. Awesome. Anything else on this last one here that maybe I went through a little bit too fast? Yes?
Is there a way to graph that curve on the side?
Graphing this curve would mean you'd have to solve for y. So if you did solve for y, you could graph it. Solving for y, you'd move this to the other side. It'd be 8 minus 2x, then you need to take the square root. So if you really were determined to graph that, here's what I would do. Let me clear out both of these. In the first function, I'll type in, let's say, square root of 8 minus 2x. And then I need the opposite of that too. I need the negative square root. So it's the negative key. And I'm just going to get a little fancy here. Instead of typing this in again, I'll hit the vars key, y vars, and tell it to take, just take the negative of the first one. And then the other graph would be y equals x. As far as a window is concerned, probably, let's see, window. Let's do like -5 to 5 on the x-axis, and maybe -5 to 3 on the y-axis. So that should probably be somewhat reasonable. That's not too bad. Okay, so you could do it. It's just a little bit more work because you'd have to solve for y. Thanks for the question. Anything else? Okay.